In this video we will be introducing calculus, which is often called the mathematical study of change. We begin by discussing the concept of derivatives. So far we have used functions to relate two different number spaces. Now we will use functions to relate two different functions. Let g of x equal x squared and f of x equal 2x. Let's call the set of operations that must happen to an input of g of x to get an output of f of x the function capital D. If we were thinking of it visually, what we are doing is imagining a set of operations on a u-shaped function to a function that looks like a straight line. We say that d of g of x is equal to f of x. It turns out the relationship of these two functions is the derivative operation. Imagine a particular input, x. Then imagine another particular input, x plus h. These inputs have corresponding outputs, g of x and g of x plus h. Now consider how the output changes in relationship to the inputs change by constructing the ratio of change in output over change in input. The x's in the denominator cancel and we are left with g of x plus h minus g of x over h. Finally, we consider the instantaneous rate of change by evaluating our ratio when h goes to 0. This set of operations on the function g of x is known as the derivative of g of x with respect to x. For shorthand, we often use g dot x or g prime x, which mean the same thing. Let's look at our example, where g of x is equal to x squared. Plug our input function into our derivative function, make a few algebraic manipulations, and get our output, 2x. We say that f of x is the derivative of g of x. In discovering the manipulations that relate these two functions, we can now also say that f of x represents the instantaneous rate of change of g of x. Try taking the derivative of a few other powers of x, and you'll see a pattern emerge known as the power rule of derivatives. The derivative of x to the n with respect to x is equal to n times x to the power of n minus 1. Now that we have defined the derivative function, we will look at a couple rules for the derivative. Basically, we're going to look at a system with the derivative as a function, do some algebraic manipulations, and prove some general attributes of the derivative function. The first rule we'll prove is known as the product rule for derivatives. Let f of x equal j of x times k of x. By definition of the derivative, we say that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. We then substitute j of x times k of x in for f of x. Next, we do some algebraic manipulations, starting with adding 0 in the form of negative j of x plus h times k of x plus j of x plus h times k of x to the numerator. We then split our fraction into two terms and pull out like terms from the numerator of each. Note that j of x plus h goes to j of x as h goes to 0, so we can simplify j of x plus h to j of x on the left and pull it out of the limit. Rearrange the terms for clarity, then recognize that what we have left after all our manipulations is a statement that f prime of x is equal to j of x times k prime of x plus j prime of x times k of x. Now that we have more or less proven this rule, we'll just skip any intermediate algebra and use the results in the future. The other rule we'll need for taking derivatives is known as the linear combination rule. Let f of x equal a times j of x plus b times k of x. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. We plug in our definition of f of x, and the result is the limit as h goes to 0 of a times j of x plus h plus b times k of x plus h minus a times j of x minus b times k of x. We can separate this into two fractions as the limit as h goes to 0 of a times j of x plus h minus a times j of x over h plus b times k of x plus h minus b times k of x over h. We then pull out the constants from the numerator and are left with f prime of x is equal to a times j prime of x plus b times k of prime of x. We have shown what the operations of the derivative function are and how we can interpret those operations graphically. Next, we need to consider what the inverse of the derivative function is. The inverse of the derivative function is called the antiderivative, also known as the indefinite integral. The antiderivative is the function that undoes the derivative, with a technical addendum. Consider a system with input g of x, function being the derivative of the input with respect to x, and output f of x. When we reverse the flow, we use the antiderivative. The form of the antiderivative is to write a long s followed by the input function, followed by a reference to what it is we are calculating the antiderivative with respect to. What's curious about looking at the system in reverse is that we see that the right side contains less information than the left. A derivative will always contain less information than the initial function. Let's take our example function to illustrate. If our input is x squared, our output is 2x. If our input is x squared plus any constant c, our output is 2x. If that's not apparent to you, convince yourself by plugging x squared plus c into the derivative function. So, looking at the system in reverse, if our input is 2x, our output is x squared plus c, where c is any constant. This means that 2x can have an infinite number of possible antiderivatives if we don't already know the value of c. When calculating antiderivatives, we'll use the relationships of input and output we proved for the derivative function, but now we just add a constant to the output. In basic signal processing, there are only a few rules, such as the power rule, you'll need to know to be able to calculate antiderivatives. We'll address them as they arise. We said the antiderivative is also known as the indefinite integral. Our next step is to introduce the definite integral, usually just called the integral. We think of a definite integral as describing some area, and we call the act of evaluating that integral integration. The area we are describing is the signed area bound between the input axis and the function. Consider the function 2x relating the input and output of a system. Let's look at the limited input span from a to b. If we wanted to describe the area bounded by the function and the input axis, we could just calculate the triangles created by our boundaries. Recall that a triangle is 1/2 base times height, so our bounded area is 1/2 b times 2b minus 1/2 a times 2a. We say minus because any area bounded between the function and input axis that is below the input axis is negative. So we'll call it the net area, which can be simplified to b squared minus a squared. In general, definite integrals are just a way to represent sums in continuous space. The representation of the definite integral is similar to the antiderivative, but now we represent bounds on the input. We write the lowest bound on the bottom of the S and the highest bound at the top. This function is a way of representing an infinite sum. It is equivalent to saying f of a plus f of a plus d of x plus f of a plus 2d of x, etc., plus f of b. I say infinite sum even though the sum is bounded between a and b because d of x is an infinitesimal step. Obviously, we can't calculate an infinite sum, so we use one of two methods to achieve the same result. The first method is simply finding the net area using geometry. It was easy in this example, but can get difficult quick. The second method is to calculate the indefinite integral, then to evaluate it at the limits a and b. We will loosely prove why this is the case in a minute. Often, if we're not already using dot or power notation, we'll write the antiderivative as a capital letter corresponding to the function being integrated. We put a line to the right indicating where we will evaluate our antiderivative. In this case, the antiderivative has already been calculated as x squared plus c. We then expand to evaluate, and we're left with b squared minus a squared, the same answer we got when we integrated using geometry. We now have the tools to state the fundamental theorem of calculus, which is just the more mathematically sound way of summarizing the last few slides. The fundamental theorem of calculus is broken up into two parts. Part 1. If f is continuous on a to b inclusive, then the function g, defined by g of x equal to the integral of f of t from a to x with respect to t, where x is between a and b, is continuous on a to b inclusive, differentiable on a to b, and g prime of x is equal to f of x. I'm going to sketch what I think are the important parts of the proof for the particular case when f is an increasing function over the interval a to b. The proof can be repeated for decreasing functions, with the results being equivalent. Basically, I want to give some intuition of why the derivative of g of x is f of x without getting too technical. Imagine an increasing function with input variable t. The function is continuous from a to b. Let's define a few constants in relationship to each other. X is some constant between a and b. X plus h is less than b. T is greater than or equal to x and less than or equal to h. And the difference between f of t and f of x is less than some constant epsilon. Our last inequality can be rewritten as f of t minus f of x is greater than negative epsilon and less than epsilon, which we can rearrange to say that f of x minus epsilon is less than f of t, which is less than f of x plus epsilon. The next step is to integrate over this inequality from x to x plus h. Remember, the only variable is t, and the other letters just represent constants defined in relationship to each other. So f of x is just a constant, meaning that the integral of f of x minus epsilon from x to x plus h is the area of a rectangle with width h and height f of x minus epsilon. The middle term of our inequality is the area bounded by the function and the input axis. And the right-hand term is the area of the rectangle with width h and height f of x plus epsilon. Do some algebra on the inequality by dividing each side by h, then subtracting f of x. At this point, let's do an aside. We need to expand the integral. F of t integrated from x to x plus h is the same as f of t integrated from a to x plus h minus f of t integrated from a to x. By definition, g of x is equal to the integral of f of t from a to x with respect to t. Therefore, g of x plus h is equal to the integral from a to x plus h of f of t with respect to t, which means our expanded integral can be written as g of x plus h minus g of x. Let's plug this term back into the inequality we've been manipulating. Now, we're going to shrink everything down by taking the limit as epsilon goes to 0 and h goes to 0. The limit as negative epsilon goes to 0 is just 0 minus some infinitesimal number, so we'll call it 0 negative. Similarly, we'll call the limit of positive epsilon going to 0, 0 positive. The limit as h goes to 0 of g of x plus h minus g of x over h is the definition of the derivative of g of x. The only way this inequality can be true, given our own definitions, is if g prime of x minus f of x is equal to 0, meaning that g prime of x is equal to f of x, and we've loosely proved part 1 of the fundamental theorem of calculus. Part 2 of the fundamental theorem of calculus is a bit easier to prove, especially if we take for granted part 1. Part 2 states that if f is continuous on a to b inclusive, then the definite integral f from a to b is equivalent to capital F of b minus capital F of a, where capital F is an antiderivative of f. To prove this, let's begin with our definition of g of x from part 1, stating that g of x is equal to f of t integrated from a to x with respect to t. Define a new function h of x equal to g of x minus f of x. Take the derivative of this new function, which is equivalent to g prime of x minus f prime of x. From part 1, we showed that g prime of x is equal to f of x, so we'll plug that identity in. By the definition given above for capital F, we can say that the derivative of capital F is f. Therefore, h prime of x is equal to 0 for all input from a to b. Remember that the derivative function measures how a function's input-output relationship changes with respect to input. So if the derivative of a function does not change over a span of input, the function is constant over the span. Therefore, we can state that h of a is equal to h of b. Write out what h of a and h of b are by our original definition of h, then equate them. Rearrange the terms to state that g of b is equal to g of a plus capital F of b minus capital F of a. Then plug in our definition of g from part 1. The final bit is to recognize that the integral of f of t dt from a to a is 0. This should be intuitive since definite integrals calculate area, and the width of the area we're calculating is 0. To summarize, the derivative is a set of operations on an input function that results in an output function. If we call the input g of x, we define the operations on the input as taking the limit as h goes to 0 of g of x plus h minus g of x over h. The power rule for derivatives states that the derivative of x to the n with respect to x is n times x to the power of n minus 1. The product rule for derivatives states that if f of x is equal to j of x times k of x, then f prime of x is equal to j prime of x times k of x plus j of x times k prime of x. The linear combination rule for derivatives states that if f of x is equal to a times j of x plus b times k of x, then f prime of x is equal to a times j prime of x plus b times k prime of x. The antiderivative is a function which performs the inverse operation of the derivative. The definite integral is a function which takes as input another function and the domain of that function, and outputs the net area bounded by that function. The fundamental theorem of calculus states that if we define the definite integral from a to x of f prime of x dt as g of x, and the definite integral of f of t with respect to t from a to b as g of b minus g of a, then the derivative of g is f, or equivalently, the antiderivative of f is g.